Hello, my name is Wesley Costa, and I'm the corresponding author and the presenter of this research entitled Increasing the LED Bias Point of an Ofdm-Based VLC System Through Multi-Objective Optimization. This work was produced by the Communication Systems and especially Visible Light Communication researchers of the Telecommunications Laboratory, LabTel, of the Federal University of Espírito Santo. Now I'm going to present the agenda of this presentation. At first, I introduced the motivation of the research, the implementation of VLC, the problems, and some approaches used in the literature, like the modulation and parameters. Then the methods used in this work are presented. After that, the application of the method presented culminating some results to be discussed. And to finish, the conclusion this work are shown. Did eventual technologies such as Internet of Things and 5G increase the usage of radio frequency spectrum? And this usage can grow and cause radio frequency interferences, called the radio frequency spectrum crunch. The development of light-emitting diodes in the last decades and the increasing of radio frequency spectrum crunch paved the way towards complementary communication technologies. The visible light communication system is emerging as a viable system to surpass the radio frequency spectrum crunch because it doesn't use the radio frequency spectrum but the optical. And more, it offers low energy consumption, communication security, and high data rates at short distances in an unlicensed spectrum. We can increase the VLC performance by adding the orthogonal frequency division multiplexing, also called OFDM. With that anti-carrier modulation, we can increase the spectral efficiency and add robustness against anti-path phenomena that also affects the VLC systems. But the OFDM-based VLC system has sensitivity to distortions caused by nonlinearities introduced by bias in the LED close to its nonlinear region. The direct current is usually recommended in the linear region of the LED's characteristic curve. So increasing the magnitude of the modulating signal will drive the LED to its nonlinear region, thus distorting the output of optical signal and limiting the optical transmitted power. In addition, the intermodulation distortion, called IMD, degrades system performance and enforces the optical guard bands that reduces the spectral efficiency. Those mentioned trade-offs suggest parameters optimization through robust algorithms that should take into account the signal bandwidth and the central frequency of the signal, as well as the guard interval that's responsible to eliminate the intersymbol interferences in the OFDM systems. There are three main optimization works used as background for this work, all done by our team, but all of them were trying to optimize the optical fiber systems. With that, we can prove that optimization can be a great method to improve the OFDM-based VLC system as well. Now I'm going to present a methodology of this work. At first, we consider an environment with a VLC system like this in this figure, but just the line of sight. The S of n here is the signal to be transmitted. And to establish the relation of the maximum value of the signal and the polarization current, we describe the optical modulation index as OMI. This blue shade area illustrates the signal to be transmitted S of n. The signal to be transmitted needs to be amplified and of course guarantee the optical modulation index. So for that, we can multiply the signal by an alpha gain and then we can add an bias current to transmit the signal to the LED. And then we have an optical to electric conversion that is expressed by this curve. And this curve is a nonlinear curve that is expressed by this equation. And in this case, we have zeta as an adjustment constant. Pmax is the maximum luminous intensity emitted by the LED in lux. And K is the new factor that adjusts the smoothness of the intensity saturation. In this case, as I've already told, we consider only the line of sight path. So we just consider the C gain, in this case h of 0. The parameters used in this work are shown in this table. This is the orthogonal frequency division multiplexing block diagram. And as we can see here, I use the Hermitian symmetry for the simulations. And here we have AIM modulation to get the passband signal. And then we can amplify the signal by this multiplication. And then we add a offset current here, as I just described. And here in the reception, we have a intermodulation distortion that distorts all the signals that has a little guard band, and then we can't receive the signal with a good performance. In this case, we consider a bandwidth of 10 megahertz, 512 IFFT points, 256 data points, because we're using the Hermitian symmetry. The mapping level here is 4 and 16 km. In this work, we consider multi-objective optimization, as I've already told about the trade-offs. This is the minimization of the guard band and the minimization of this SNR for a bit error rate of 10 to the minus 3. For these two objectives, we need to optimize other variables, that is the optical modulation index from zero point 0.1 to 1, the bias current that varies from 400 to 2 amperes, the guard band, the guard interval, and the upsampling factor. For that, we need a multi-objective optimization algorithm. And in this case, we consider a robust algorithm that is called NSJ2, that is the dominated sorting genetic algorithm. In this algorithm, the solutions are categorized by the dominance conditions and form groups of fronts that is called Pareto fronts. We say that one solution X dominates another solution Y if X can be worse than Y in all objectives and X is better than Y in at least one objective. In this case, the solution W forms the set of the first Pareto front that is the solution that are non-dominated by any other solutions. If the non-dominated sorting stage gives us more solutions that was established by the parameterization of this algorithm, we need to use the crowding distance sorting that will rank the solutions by their distance. And then we can have a diverse set of solutions using this equation. And then we need to reject the solutions that pass the number of the solution that was established at the start of the algorithm. So this is the overview of the methodology. We used here the VLC channel. So the VLC system was used in this work. The modulation used here was the orthogonal frequency division multiplexing with the Hermitian symmetry and AM modulation for the passband signal. And we used then a multi-objective optimization to minimize the SNR for a bit error rate of 10 to the minus 3 and to minimize the guard band and avoid the intermodulation distortion. So in this case, we had two objectives and we have five variables. There was the optical modulation index, the bias current, the guard interval, the sampling factor, and the guard band. In the conducted Monte Carlo simulation, the bit error rate was used as figure merit in this performance evaluation. The real-coded NSJ2 algorithm was implemented as described previously. The initial generated population started with 20 random solutions for optical modulation index, I bias, band guard interval, and upsampling factor. The use mutation rate was 0.02, the crossover at rate of 0.95, and we used the tournament selection. The first Pareto front generated by the optimization is shown in this figure for 4 km and 60 km as subcarrier mappings. It can be seen that the SNR required for a bit error rate of 10 to the minus 3 decreases when the guard bands increases. This is explained by the intermodulation distortion caused by the photodetection. This effect is pronounced when the guard band over the bandwidth is 0.05 for 4 km mapping. This table shows the optimized parameters obtained by the first Pareto front. For 60 kAm, the SNR needed for a bit error rate of 10 to the minus 3 vary from 18 decibels for a relation of the guard band bandwidth of 0.01 to 15.5 for a guard band and bandwidth relation of 0.87. In order to analyze the impact of SNR with respect to the DC current, this figure shows the SNR penalties, which is the difference between the SNR required for a bit error rate of 10 to the minus 3 and the optimized bias in the VLC system with the parameters shown in the third line of the last table for both 4 and 16 kAm. The bias was varied from 400 to 2000 milliamperes, and as can be seen, the SNR penalty increases with the bias current because of the LED's nonlinearity, as you can see here, which increases for a bias greater than 750 milliamperes. In the linear region, which is for bias lesser than 550 milliamperes, the penalty changes are not expressive. So the conclusion and future works. In this work, the bias current modulation index in the guard interval and the guard band was optimized in order to minimize the signal-to-noise ratio required for a bit error rate of 10 to the minus 3 and the up to guard band. The simulation results showed that the SNR decreases with the guard band reduction. The guard band of 1% of bandwidth was achieved for SNR values of 14 and 18 decibels for 4 and 16 km respectively. The SNR penalties increases with the LED's nonlinearity region for fixed parameters and varying the LED bias current. And for the linear region of the LED, the variation of the SNR wasn't expressive. For future works, we tend to validate the optimization procedure through experiments, and we want to make more optimizations in a non-line of sight VLC channels. We would like to acknowledge the funding agencies in Brazil, CAP, CNPq, and FAPES, and the projects that we've enrolled, like Núcleo de Estudos em Tecnologias Emergentes para 5G, NEST 5G, Aplicação de Tecnologia de Comunicação por Luz Visível e Monitoração de Recém-Nascidos de Alto Risco, and the Brazilian and Germany project called Optical Wireless System with MIME architecture in an industrial environment called OWIND. This is the references used in this work. That's all. Thank you very much for your attention.